All right. So we stopped, discussing on this random walk, and what I tried to demonstrate was that if you have a random walk with absorbing nodes, or random walk with absorption, you can actually calculate the probability of absorption on those nodes. And you can do it just by taking the matrix and putting it into their nth power, right? And going limiting and going to infinity, or as shown here, it was lim p times to the t. Now, what's interesting is you do not really need to do the sort of numerical computations as I done with a simple network. You can show in general that this is what's going to happen, that the matrix will take that form if initially, before doing the computations, you actually number the nodes such a way that absorbing nodes are the first nodes in the matrix. So if you actually start with this type of the matrix, where you have the first nodes in the graph, or the first rows and columns in the matrix, will correspond to absorption, right? Absorbing nodes. Then the nodes here, they correspond to the nodes that are not absorbing and transition from them to absorbing nodes. And here, probability of transitioning, one-step transitioning from unabsorbing nodes to unabsorbing nodes. Now, in our language, absorbing nodes are those nodes with labels. Unabsorbing are unlabeled. So P U sub L means unlabeled node to labeled node, and P U sub U, P sub UU, it means a probability going from unlabeled to unlabeled. And one can show that, and I'll have to clean this up a little bit. So one can show that at the limit of large time, multiplying this matrix by itself, you will get that. And you can actually easily do it by just literally taking that matrix and multiplying by itself, and multiplying by itself. You can multiply matrices when they're written like this as a block matrix by multiplying blocks. And so if I write down right now this block I0, PUL, PUU, and another one I0, PUL, PUU, and multiply them, then, for example, clear multiplication of this row by this column will give me just I, right? Multiplication this by this will give me 0, and you can calculate the multiplication of the second row by the first column and the second row by the second column. And if you assemble all of them together, just by purely multiplying them through, you will get this matrix. And the trick here, the very last trick, is the following. You probably remember from somewhere that if you take, say, 1 divided by 1 minus x, what does it approximately equal? Where x is small. So the ratio 1 divided by 1 minus x is approximately equal to x, right? If you take this as a Taylor series expansion, you can actually see that if you take it like really, calculate through derivatives the expansion, you will have this x to the n, and I'm sorry, it's not x, is, what did I say? I said x. 1 minus x is equal 1 plus x, right? What I was trying to say is equal 1 plus x, right? So you take Taylor expansion from 0 to infinity, that's what it is. So you can actually do the same stuff with matrices. And so what is done here is the following. This is right here. And so you can assemble it back together into this 1 divided by 1 minus x version. And that's what's here. Okay? So that's the whole point. You can actually calculate those limiting probabilities by multiplying matrices, and a lot of things will sort of converge, so you don't need to write sums. Okay. Oh, and the very last point is this guy is actually 0. Now, the reason for that is because this is a subset of the transition matrix, and in general, because this is a transition matrix, the whole thing ends up to 1, but this subset adds up to less to 1, and which means if you start multiplying by itself, numbers that are less to 1, eventually you'll get 0. And so that's why this becomes 0. So the point is, the reason for that sort of exercise and dividing the matrix into these 4 blocks with absorbing and non-absorbing nodes is that when you take this to the nth power, or look at the infinite time, the matrix will eventually just look like this. So this matrix is P to the T, where, well, this, okay, this is lim T goes to infinity. So back to our story, we had like this, little 20 minutes discussion of random walks. Back to our story, if you take this matrix and put it to the power t, and which means you want to calculate the probabilities after t steps, and take t to go to infinity, the matrix eventually will look like that. Now, if I split the matrix into those blocks that corresponds to transition from labeled to labeled nodes and from unlabeled to labeled, I can write the equation y equal e infinity. Why? I can write this equation in the matrix form. So the labels here are just split into the labels that we know, y sub l, and the labels that we don't know, y sub u. And this is the thing we need to find, and these are the given to us things. And y sub l are labels known, y sub u unknown. In order to calculate those things, we can actually need to equate unknown to something. It doesn't really matter to what. You can actually just use this vector. Now, because of the block structure, what you can instantly see is the labels on, well, labeled node, because of our procedure, will not change. So this is equal to this row times the column. Well, nothing changes because there is 0 here. And the unlabeled nodes can be obtained by applying this equation. I mean, by applying this row to this column. I just multiply through, I get this. And that's sort of the core. So what it says is the following. To calculate the labels for the unlabeled nodes, I need to take the labels for the labeled nodes, those that are given to us, multiply by this part of the matrix, which is a probability of one-step probability transition from unlabeled to labeled, and multiplied by inverse of this expression. So what's encoded here again? PUU is a probability of transitioning between unlabeled nodes, and this is a probability of going from unlabeled to labeled node. It is one-step probability matrix. So this is for those nodes that are really connected to labeled nodes, and this spreads the influence to all unlabeled nodes. That's sort of how you understand this this matrix, this equation. And in fact, this is pretty much the solution. So if your matrix is small enough so that you can actually calculate the inverse, you're done. Okay? So pretty much all this math we talked about leads to this equation. So eventually, this is your sort of, this is the result. You take the matrix, you calculate P, which is D minus 1A. You split it into pieces. You split it into these 4 pieces, labeled, unlabeled. And then the solution, the label propagation algorithm, can be written in this form where you don't need to do any iterations. It's just one, step solution. So that's sort of the ultimate result of our discussion. All right. Now, the trouble here is that for large graphs, doing this inverse can be hard. It's an inverse for a large sparse matrix. So, in fact, it's much better to do some iterative algorithm that will compute this value for you, instead of just doing inverse. But again, if your matrix is like size of 100 or something, you're playing around with it, you can just do inverse in MATLAB or Python, R, whatever. It works. So it happens that the following algorithm will actually converge to that solution. So the algorithm is very, very straightforward. So you take your adjacency matrix that describes the graph. Okay, some nodes are labeled, some not. You compute the diagonal for this matrix. The diagonal matrix, which is a degree matrix, right? So you add up node degrees, the same way as PageRank, and compute this transition matrix, D minus 1A. It is, again, the same stuff we did with PageRank. We then initialize labels all over the graph, and those that we know, we assign those values. Those that we do not, we just put 0. It doesn't really matter because it did not affect anything. The reason they're not affecting anything, again, if we go back here, this is this unlabeled nodes, their initial labels. If you notice, in the final result, they're not playing any role because this column, the columns here are 0. So this thing doesn't really matter. Anyway, so you can initialize to whatever you want, and then you just run the following iterations. You just take the label vector and multiply by the transition matrix. And then you forcefully set labels on the nodes that you know not to change. So those the labels on the nodes that already have known labels, they fixed. They do not change. And we calculate in this iterative fashion only labels on the unknown nodes. And that's pretty much it. And you just iterate this until the labels stop changing. Now, this procedure, this iterative procedure, is what's called label propagation algorithm, and it allows you to compute the labels as we discussed. So you can easily show it for yourself that this type of iterations they actually give you exactly the same solution. The way to show it, well, this is your type, this is your iteration. You can write this iteration again by splitting the matrix into this sort of 4 blocks. You can write it in the following fashion, and then what you do is, like, sort of as you do always in this type of recursive forms, you write this is the same thing for t minus 1, for t minus 2, and just sort of keep substituting it back. You'll get this expression, and that expression can be easily evaluated to lead this. And that's sort of what we had a couple slides back. So these iterations allows us to solve to find the labels using iterative methods. Bottom line, with this label propagation algorithm, what we're trying to do is we're trying to simulate random walk. And when we're simulating random walk, we're calculating the probability that the random walk that starts at n node will end up at the node with a particular label. And those nodes considered as absorbing nodes, and we can calculate those probabilities of absorption. And that can be done either sort of in one shot by inverting the matrices, or it can be done through this iterative algorithm where you just need to do multiplication. So in both cases, it's trivial, and it works like a charm. Okay. So if you're thinking about sort of the workhorse algorithm, that is the algorithm that I would recommend you to use. Now we'll see at the end, we'll see that in fact this algorithm is, under some conditions, is pretty much exactly the same as this iterative algorithm we started the lecture from. And it is literally does the same thing of averaging values on the neighbors, but just in a sort of smarter way with renormalization that guarantees that the whole thing will converge eventually. Okay? And you can apply it to directed or undirected graph. If it is directed graph, you have to be more careful, because you need to have a strong connectivity, so things will propagate. But typically, we look at undirected graphs in this case. Any questions about this algorithm? Well, except for little details, how you multiply matrix, you just, again, if you do not get that, you have to actually just do it once yourself, just by hand, like literally write the matrix and see how things get multiplied. The general setting is clear? Okay, so now this one you will have to implement. It will happen next time, but just be aware. Okay, there is one thing in this algorithm that may be, well, not perfect. Well, actually, there are many things, but so one thing that sort of jumps at you is the following. This algorithm does the following. So when we calculate the labels, and I'll call them y hat, the final labels, here we get sort of predicted labels, and here we start with original labels. So what it does is, again, those nodes that originally had some labels, and again, I will just draw them as the colors. It could be, probability distribution, whatever. So we predict using this algorithm labels for unlabeled nodes, but it will keep the labels for known nodes fixed. So they will not change. Okay? Now, it might be a feature. It might be a good feature because you say, okay, well, we did a great job labeling nodes, and I don't want your algorithm to change the given to you data. But on the other hand, the data that you get in real life often noisy. And so it might happen that your labeling, your original labeling, is inconsistent. What I mean by that is, imagine that, again, we have a graph, and we have situation like that. Say there is some group of nodes, and let's say all these guys are red, and there is connection everywhere, and this guy in the middle is green. According to our theory that similar nodes need to be connected with similar, this is a little bit strange situation where you have a green node connected to red nodes completely, right? So it would make more sense if the central node would be green, would be also red. And this algorithm labeled propagation cannot do anything. It would say, okay, well, this is the data given to us, that's it. But you can again think that data can be noisy, and this green in the center, well, supposed to be actually, this guy supposed to be actually red, but we have noise in the given data. And so we can actually ask algorithm, while it does the label propagation, to also update this guy, to be consistent with the neighbors. Okay? So we can actually try to have an algorithm that also improves the given labels. Here is a formulation of that type of algorithm. In fact, okay, this is done by very different guys, though the last name is similar, so there's no mistake here. If you notice, this guy is Zhu, he is from CMU, this is Zhao, and co-authors there from, I think, Fraunhofer Institute in Germany, so different groups. So the point of this algorithm is the following. It should remind you a little bit of the page rank, or like personalized page rank. So when we do iterations, and in every iteration we consider sort of random walk, but we also, with some probability, have an extra step. So what this algorithm does is the following. There is a walk matrix, and now it is slightly different from what we did before. On the previous algorithm, we did walking matrix was D minus 1, A. Here, it is D minus 1/2, A, D minus 1/2. Now, there is some reasons why they choose to do that type of walk. It's not exactly sort of our simple random walk. It's just somewhat different. And they also do the following. On the iteration, they do this random walk step with a probability alpha. But with a probability 1 minus alpha, there is sort of jump back to initial labels. So if I'm thinking about labeling, the labeling becomes a mix of the labeling due to the random walk and it mixed sort of original labeling all the time. Now, you might ask why in the world they came up with this idea. Well, there are some ways to think about it, and again, in a few slides, we'll have a very generic, way how you can derive these algorithms. The point here is you're actually mixing up updated labels on every step, and you're every time adding sort of a little bit of original label. Okay? The intuition comes from the sort of the page rank process. And you do it until things converge. So again, for you as a person who's going to use those algorithms, the difference here is the following. This algorithm will actually change the labels on those nodes that were given to you as labeled. It can keep them the same, or it can adjust them based on the consistency with the rest of the graph. And this algorithm has a parameter alpha. So depending on this parameter, you might get slightly different results. So you need to, you should be able to play with this parameter. But overall, it is very, very similar algorithm. Now, we need to make sure that these iterations, they actually converge, right? And you can easily show that they do converge. Here is, that iteration written out. If we take, here it's much easier than the previous case to show that this thing converges. You just take a limit going to infinity. This also becomes the sort of the final value. Here they are. Here they are. This is this. This is that. This thing remains. And so you can easily solve this by inverting. And by the way, I missed here to the -1. So this is the inverse of this matrix. -1. So the reason is because what I do here, I take this on the left side, and it's going to be y hat minus alpha s y hat is equal 1 minus alpha y naught. And then you can and that's how you solve it, right? So here is also sort of one-shot solution. And again, it works if you can invert this matrix. If this matrix is small, you can easily invert it. Now, parameter alpha can help you invert the matrix if, for example, so parameter alpha can make some matrices invertible even if they're not originally, right? Again, it's in this sense, it's very similar to what happens with PageRank. So if the graph is small, you can just do this solution, one-shot solution. If the graph is large, you do iterative process. Now, the difference with what we did before with the sort of label propagation is, in this case, we do change labels for all the nodes. Notice that there is no split here in between labeled and unlabeled nodes. You start with unlabeled node, with a vector, with initial vector, where you put here labels. Then for unlabeled nodes, there will be zeros. You iterate, and you get the final vector of labels for all the nodes. And these labels that, there are sort of labeled and unlabeled nodes, and the values on the label nodes will also change, or might change if they're inconsistent. I shouldn't say that they will change. They might change if they're inconsistent. Okay? Questions about this? So it is an iterative procedure with slightly different iteration matrix. And it's called label spreading, or sort of another label propagation algorithm. Okay. Now, all these algorithms, the one we sort of looked at, and there are many more of this type of algorithms out there. They all sort of try to achieve two goals. They want to predict labels that, on one hand, consistent with initial labeling, right? So if you have a graph with labels, and here is your green labels, and here is your red labels. So what you're trying to do is, first of all, you're trying to predict a label that is for those nodes that are in that case is where you're predicting labels for the node that are already labeled. You don't want the sort of new labels be very much different from what the given data was, and so that there is always this. You might want to use this type of distance metric in between new labeled node and sort of old labeled node. And you do want to make sure that there is some sort of consistency in between nodes that are connected, in between labels of the nodes that are connected. So this is a label of one node, this is a label of another node, those two nodes are connected. So if the labels are different, we can, that's sort of bad, right? If the labels are the same, that is good. Think about this as a sort of regression function. What we're trying to do, we have a bunch of points, and you're trying to regress on them. So on one hand, you're trying to match to the values that they're there. On the other hand, you want to make sure that when you're regressing on the nearest neighbors, when there are sort of the values on the nearest neighbors, they're similar. So the similarity on the nearest neighbors really means the smoothness of the curve. So if I, for a second, forget about graphs, right? And let's say I have just sort of traditional regression problem, right? We have a bunch of points, and I want to do a regression. And I can do regression, if I do a straight line, it will be something like that, right? Or I can just go for a higher order, something polynomial, right? Or I can actually build it like from linear fragments, sort of interpolate between points. So this will make my interpolation be close to the original points. This will make my interpolation look smooth, because it will just say, okay, it shouldn't change a lot on the neighboring points. We're not allowing jumps. So this is a smoothing factor that is a matching to the data. And you can also, in the tradition of sort of regularization, you can also, use the term that just tells you, okay, well, you do not want, the labels, if the labels have the probability to just become very large. So what I'm trying to say is the following. You can actually build some function, some sort of error function, right? Can call them E of Y, as a combination of this parts that gives us consistency with initial labeling, and something that gives us the smoothness. So we can actually write this as, okay, we'll have something like that with a quadratic function with respect to Y. We can have this function that tells us how far we are on the labels, and we can also have something like that here. And again, in tradition of this sort of regularization research, we can put here, say, some parameters that you can optimize. So what I'm saying is you can actually assemble some energy function that you can minimize to find the best labeling. And this energy function will contain different terms, will contain the term that matches, that allows you to match your sort of function to the labels that are given, and will contain a term that will tell you that your function should be smooth. So this term, in fact, this Y transpose Ly, where L is Lagrangian, it is equivalent to the second derivative if we're talking about sort of continuous representation, right? And we did that a bunch of lectures ago when we talked about diffusion on graph. So we talked that diffusion would be described by the Laplacian matrix, and the Laplacian matrix comes from the idea that it takes second order derivative, et cetera, et cetera, et cetera. So this term is a smoothness term, corresponds to the second order derivative to make sure that the interpolation across all the nodes is smooth. this term gives you the similarity, gives you the closeness in between the labels you're predicting and the actual given labels. All right. So in terms of regularization, this is the term that makes you go through the points, and this is a term that makes your regularizer curve smooth. And it's just written in terms of the graph, okay, taking into account the graph structure. And based on that, you can easily imagine that you can really, just solve the optimization problem and find the best labeling that will optimize, it will minimize this, energy function. And in fact, that's what's typically done. And moreover, the algorithm that we talked about, they can be derived from this. So this label propagation we talked about, the random walk, right, with absorption, it really corresponds just to optimizing this. So to optimizing, the smoothness. Remember, in this label propagation, we did not allow labels on the known nodes to change. And so the algorithm just optimizes this energy function. Now, how do I know this? Well, I will not derive this completely, though you can easily derive it yourself, but just sort of think about this. If this is the functional we want to minimize, so what we want to do is we want to dq dy equal to 0. And I'll do dy transpose equal to 0. Now you can do it very carefully, or you can do it just sort of skipping some steps. But if you take this quadratic form and differentiate with respect to this guy, it will just be this L times y equal to 0. Right? It's all matrices. And matrix L is a Laplacian matrix. So it is d minus a times y equal to 0. And I can write it right away that it is d y equal a y. And now if I write it through the nodes, it will be the following: di, which is a node degree, times the value of the label on that node, is equal to aij yj sum over all j, which gives me yi is equal 1 over di sum of j aij yj. So what this says is the following: if I want to minimize this functional, the minimization happens, well, it's a Laplace equation, and the minimization happens when I calculate for every label yi, I'll just take the average of its neighbors. And that gives me the minimum of this Laplacian. So in some sense, we pretty much all day, all lecture, we're doing this kind of idea. Take the nodes and average the values on the nodes to infer the value, the label on the central node. So the label here will be inferred from the nearest neighbors by averaging. We in fact started with that algorithm. So that algorithm is derived from optimization, or can be derived from optimization of this functional. The second algorithm that we looked at this label spread. One can show that it really comes from optimization of this guy. It's a little bit different from this. Again, for those of you who are interested, take a look at in the references. You will see how this works. But the point is, it's also an optimization procedure. You take it, you optimize, you'll get the solution that's given to you by this label spread. And so you can actually create lots of algorithms based on looking and optimizing the various form of this functional that combines smoothness and match. I'm going to talk about one more algorithm just because it gives you a little bit different flavor. It actually optimizes this functional that has the smoothness criterion and the matching criterion, the matching on the nodes. If you remember a little bit of differential equations, partial differential equations, right? There are several ways to actually deal with them. One way is integrating the differential equation, right? What's sort of the other way to do solutions for the differential equations, whether the partial differential or whatever? So one way is doing integration. Another way is dealing with green function, right? And a green function, in some sense, that approach is really is about eigenvalues, eigenvectors. So what you can do is you want to solve differential equation. You can find an eigenvalue. You can find the basis, eigenvalue basis of the operator that is in the differential equation, and then look for the solution in that basis. Okay, any recollection about those kind of things from differential equations? Yes, no, too far off? Okay, so again, when you do, well, even if you don't know it, this is pretty much what you need to know. The idea is the following: you can look for the solution by finding the eigenvalue, by finding the eigenbasis of the operator in that equation, and looking for the solution within that basis as a linear combination of the vectors in that basis. It is somewhat similar to, if you want to do, I'm sure you solved differential equations or partial differential equations when you took, like, say, Fourier basis, and you were looking for the solution in that basis, and the solution will be coefficients in the Fourier basis. So, cutting this short, the point is the following. In this case, the key operator is this Laplacian. And so we have Laplacian matrix. We can find eigenvalues, eigenvectors of that Laplacian matrix. And then we'll try to find a linear combinations of those eigenvectors to match the labels. So we'll express labels, given values, through the linear regression over eigenvectors. And if we can compute those values, that gives us a linear combination of eigenvectors, then we can predict unknown value easily by taking linear combination with the parameters we have found. So that's the idea of the Laplacian regularization algorithm. So what you do is you compute, again, you take the matrix, you compute diagonal, and you compute Laplacian. It's the same Laplacian as we used in spectral graph theory when we tried to calculate graph partitioning. And we compute p smallest eigenvalues. Again, remember, the second smallest eigenvalue in that case was giving us graph partitioning. Here, we compute the basis of eigenvectors, not only the smallest one, but the p of those. And we try to use them, as a basis and calculate the linear combination of them that will give us known labels. This is local, it's a regression problem. And the solution for that regression problem is given by sort of standard regression solution, which is you take the you take the matrix, take inverse, etc. So it is a minimization here, and as a result, we get those coefficients A. And if you want to predict unknown labels, use those coefficients with the values with eigenvalues, well, with the values of the eigenvector for those nodes to predict the value. Okay, we are now pretty far in the lecture, so probably this goes like that. Take a look at this algorithm. It's actually a sort of follow the tradition of partial differential equation solutions. Again, the whole goal is to compute eigenvalue basis of Laplacian operator, and then take, then look for the labeling function in that basis, within that basis. So use that basis to linearly reproduce the ranking function, and then you can do prediction. So it's sort of mixture of this regularization approach where you do eigenvalues, eigenvectors, and then there is a little bit of regression in here. Here's just an example of simple label propagation. I start with, this is algorithm number one, the one we just did. Number one, which is the simplest one where you're just averaging. So here is a bunch of nodes. They're unlabeled. Again, the whole trick is that you do have a very few labeled examples. This is Zachary Karate Club graph. Assume that if there is a connection, there's similarity between nodes. I just sort of labeled 3 nodes as red and 4 nodes as blue. And then I run this label propagation. Here is what I get. Now, I color-coded it according to the probability to be one class or another class. And, color-coded like going from red, to blue, right, the color scheme. And so the dark blue means, this class, and dark red, we're here. And there is sort of color interpolation, like sort of traditional color interpolation in between. So what you should see here, what you should notice here is that, because of the way the algorithm works, the original nodes preserve their labels. And it's clear that for some nodes, like right there, labels will be probably more blue than red. And for these guys that are closer to red but far from blue will become blue. And for those nodes that are in between red and blue, the label should be sort of colored in between, because again, I color the probability of the class, right? So, and that's what we see. We have here a bunch of dark red, dark blue, and this node, for example, sits in between the dark red and blue, so it has some color in here in between the gamuts. And the closer to the red world, the redder they are. So it does what it's supposed to do. Interesting point here is that if you remember, we use this graph also for graph partitioning. And these problems are somewhat similar, because what I've done here, in fact, I set up nodes here in sort of one cluster, and this nodes is set up in a different cluster. If you remember, the graph partitioning would give us this type of split in between clusters. So, and I sort of initiated one type of node in one side, another type of node in another side, and so what we got eventually is almost clustering graph partitioning, right? So we have all the red nodes here, and all the sort of the blue nodes are here, so we almost got 2 clusters. So in some sense, these are very similar problems. Propagating labels and graph partitioning. If you think about that, you can come up with original, so with some sort of initial labels, you know that this node belongs to one partition of the graph or one cluster, and this node with this label. So label can be just the fact that the node belongs to one of the clusters. So this belongs to one cluster, this belongs to another cluster. Find me the rest? Well, since we're using graph structure, we'll get the graph partitioning network communities thing. And just out of curiosity, I take the same graph and I set up the initial labeling slightly different from this, cluster structure. And what would you expect here in terms of labeling? Notice that red nodes in some way blocking blue nodes from spreading, right? So red nodes sit here on all the sort of connections that go out there. So blue node, there is really almost no way for blue node to propagate beyond this boundary. So this red node's blocking them. And if the algorithm runs correctly, what you would expect is this should be some sort of red, and this will be like little blue color. And when I run this, that's what you get. You really get a bunch of reds here, and blue influence is pretty much bounded here and a little bit here. So, and this is again the simplest label propagation scheme. Okay, that's it for today. It was a long lecture. The bonus is you do not have a lab after it, but you will cover some of the methods next time. If you're interested in this, there are several pretty good reviews. The first review is about the iterative classification, sort of a classical iterative classification we started the lecture with. The second couple reviews, they are more on this method. Well, actually, the second review is totally on semi-supervised learning with graphs. The third one is touches upon everything, and here's a few original papers if you're interested in. So that's it for today. Questions?
I have a question. Is there a model? Initially, during your lecture, you started talking about this machine learning approach, where you discussed this using labels of neighbors as features. Is there a model, or have you seen one, which models unlabeled graphs, unlabeled vertices using latent variables, and then does some kind of either Bayesian or Monte Carlo or EM algorithm learning on that thing? So basically what I say is that all unlabeled vertices are latent variables, which we are to predict from the graph we have. So this way we retain your brilliant idea of keeping the information from neighboring labels and achieve the goal.
Yes, it's a very good question, and I would guess, do you guys have the class in Bayesian networks?
Not in Bayesian, but we are familiar with EM algorithm and probably Monte Carlo.
Okay, so there is entire. We didn't touch upon it, but if you look in the reviews, yes, there is entire sort of. There are several directions in this field, right? We touched upon one of them that has to do with semi-supervised learning and the diffusion processes. I talked a little bit about the sort of the classical approach, and yes, there is a way to look at this, as you said, with latent variables and in general with Bayesian networks. There are a bunch of approaches, in fact, there, and they do very, very similar to what you described, which is, you set up latent variables and you look how they propagate in the Bayesian network. So the answer is yes. We didn't, talked about it today. Look in the reviews; you will see references to, the big body of literature on that stuff.
And the reviews you mentioned are listed on your slide?
Yeah, so yeah, I will have them on the website, but here they are in particular. I believe, hold on a sec, I believe these guys definitely talk about, they have references in there to the papers.
Okay, thanks.
Yeah, but that's another sort of way to look at that. I didn't touch upon them because, well, you need to talk about the Bayesian networks then, and that's a lot of things to discuss in order to make that, to understand how that works. All right, cool. Well, we're done for today. Next time, sort of typical regular lecture and yeah, and a lab after that. All right, that's it.